All right, folks, next learning goal 8.3, know how to determine a general rate law or the rate expression for any reaction. So I'm just going to set this up briefly and generally, and then we'll go through lots of examples in our live lecture. So if we consider now this simple reaction, A plus B goes to products. As we're going to see as we keep going down the rabbit hole, kinetics is all about the reactants. So I'm going to say all about the reactants, which is not to say that the products are unimportant. However, oftentimes when we're setting up our quantitative information and our kinetic expressions, we generally do something like this, as you can see here, where we're not interested in the products, we're just interested in the decay of reactants. And with that in mind, then, when we talked about how these rates go, right, negative dA by dt, which in this case would be the same as the rate of B, if we look at any point along the reaction, so for example, if I look at this point highlighted right here, the tangent to that line gives me the rate of that reaction. But if I were to look at some tangential point up here, you can see I get a different rate. Okay? So what we need is some universal thing that will describe the kinetics of this reaction for any time. And that universal thing is the rate expression or the rate law. Okay, so rate law. And the general form of the rate law is it's all about the reactants. So we say rate equals K, and that is our rate constant, which will be constant throughout the reaction. The brackets denote concentration, and we've established that in gas phase reactions, that's molecules per cubic centimeter, and solution phase reactions, that's mole per liter. And then finally, these little A's and B's right here, those are our reaction orders. So, and they are typically whole number integers, but they don't have to be. And they describe the dependence of concentration on the rate. Okay. So now what we can also see, because I wrote this generic like rate thing, so we could make the rate law equal to the rate of A by replacing rate with negative dA by dt is K times A raised to its order times B raised to its order. Or we could write that with respect to the rate of B. So I'll just put that also equal to that rate. So we can put either one of those in this expression. And as long as we've considered the right relative stoichiometric coefficients, then both are correct. Okay. So it's important to note that reaction orders are determined experimentally. Okay. Determined experimentally. In some cases, it's possible to determine them theoretically. That's only if we have detailed information on the mechanism, or if we know that this is just a one-step reaction. So for now, we'll trust this bit that reaction orders are determined experimentally. And as we go further down the rabbit hole, we'll see how they could be determined theoretically. So let's do an example, and maybe you remember this from Chem 109, the method of initial rates. And what we're trying to do here is get the rate law for this reaction by getting the orders of the reaction, and that will also eventually allow us to compute the rate constant. So whenever we're setting up a general rate expression, it's always going to be rate equals K times reactant raised to its order times reactant raised to its order. So notice I've got specific products in here, but they don't appear in my rate expression. And also, it's not necessarily true that the reaction orders are equal to the stoichiometric coefficients. So we have to see what the data tells us. So now, if we look at this method of initial rates, there's a simple way that we can put this together, and it goes as the following. So I'm going to compare experiments 1 to 2, and I'm going to do it in the following way. I'm going to write the rate of experiment 2, and you'll see why I chose that in a moment. So 2.7 times 10 to the minus 7 moles per liter per second, and that all equals K, which I don't know. And now times ammonia, its concentration was 0.100 molar, and that's raised to some power that we don't know yet. And then now multiplied by the nitrite concentration, 0.010 molar, raised to some power that we don't know. And now I'm going to divide this whole thing by the data from experiment 1. So now that becomes 1.35 times 10 to the minus 7 mole per liter per second. And that still equals K. And then now we're going to use the data from experiment 1. So the ammonia was still 0.1 raised to the X. And now the nitrite is 0.0050 raised to the Y power. So now hopefully what we can see here is the K is going to drop off. The 0.1 raised to the X power is going to drop off. And now when I look at these two numbers here, 2.7 times 10 minus 7 divided by 1.35 times 10 minus 7 is 2, and the units will cancel. And now what we end up with is 0.01 to the Y power divided by 0.005 to the Y power. And quick math reveals that that is equal to 2 to the Y power. So this means Y has to equal 1 in order for this equation to work. Okay? And so now we can do the same thing, but this time we're looking for where the ammonia concentration varies and the nitrite concentration stays the same. So that's experiments 3 and 2. And if we do the same thing there, maybe you can already see what's going to happen in your head, but all the same, let's work through it. So we've got the rate of experiment 3 over the rate of experiment 2, mole per liter per second. And then now all of that equals K. So I'll put that division sign all the way across. And so now the ammonium, I kept saying ammonia, but you can light me up in the comments. It's ammonium, 0.2 raised to the X power, and that's 0.010 raised to the Y power. And then now on the bottom, that's K. And then now we're grabbing the data from experiment 2. So that's 0.100 raised to the X power. Now you can see the nitrite concentration is unchanged. So now repeating that same process, K cancels, the 0.01 to the Y power cancels. 5.4 divided by 2.7 equals 2, and 0.2 divided by 0.1 to the X power becomes 2 to the X power. So you can see X is also equal to 1. So what that tells us now, the rate law for this expression is the following. Rate equals K times ammonium. And I don't need to write to the first power, right? We just assume that that's raised to the first power, times nitrite raised to the first power. And so now what's important to note here is its first order in ammonium, because the reaction order was 1, its first order in nitrite, because it was raised to the first power. But overall, the reaction is second order. So we add up the orders for all of the reactants to see that overall the reaction is second order. And so what that means is, for a second order reaction, if all of the concentrations double, then the rate should quadruple. And we can see that right here, right? When we go from 0.1 to 0.2, that's a doubling from experiment 1 to experiment 3. And then similarly, when nitrite goes from experiment 1 to experiment 3, it also doubles. And so 2 raised to the 2 power is 4. So we can see the rate goes up by a factor of 4 when both concentrations go up by a factor of 2. So in the preceding videos, we're now going to digest each one of these individual orders. We're going to look at 0 order, first order, and second order, and talk about all of those consequences and all of the properties of those different types of reactions. I'll see you then.